So now let's talk about one-class classifiers. And then I decided to use again the simplest one. It's called the confidence ellipse for that. The idea is following. First of all, it's a one-class classification. What it means? It means that we sort of, I wrote this outlier detection. Why? We sort of make a model only for members. So it means that training set should consist only of the members of the class. And then any non-member should look like an outlier. For example, if we make a class for apples, any pair should look like an outlier in terms of, for example, chemical composition and so on, right? Because it's a confidence ellipse, it means that we need to use a kind of confidence level or significance level if you want. And significance level will tell you the ratio of false negatives. In this case, it means that, for example, if significance level is 5%, so confidence level is 85%. So it means that we can expect that 5% of good of members will be rejected by the model. So it's exactly what we call a false negative. Then the algorithm is very simple. First of all, we need to take all the calibration objects of a given class, the training set, and we need to make a confidence ellipse around this object. And we need to compute this confidence ellipse for a given confidence level, right? And then the classification is very simple. If object is inside ellipse, it's a member. If object is outside ellipse, it's a stranger. That's it. So how to compute this ellipse and actually what are assumptions about this data, I will not tell you all the mathematics. You can use this link. You can also find it in the among course materials how to do that. But the idea is that we use covariance metrics, eigenvectors, eigenvalues, and chi-square distribution, similar to what we discussed in the PCA. In case of PCA, when I told you about Mahalanobis distance, what Mahalanobis distance is. Okay, and then this is an example. So again, in this case, I didn't use iris data. I used just the normally distributed data, two variables x and y. And then you can see I actually generated 100 measurements, 100 x and y values. And then I made 3 different ellipses. So you can see, for example, the blue ellipse, the blue one, it's an ellipse that is made for 90% confidence. So it means that for the blue one, we expect 10% of the objects will be outside this ellipse. Let's count, right? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? I'm a bit in doubt with this one, but we got 11 out of 100. So it's almost 10%. Of course, it will never be exactly 10%, especially if sample size is small, right? And then for the green one, you can see for the green one, we have 5%, it's 95% confidence. And for the red one, it's 1%. Yeah. For example, if you look at the red one, we have indeed only one outside the red one. So we have exactly 1%. Okay. So this is the overall idea. Of course, apparently, if the confidence level is large, so significance level is small, then you have a higher risk that the bad guy will be inside, right? So it means that by decreasing the amount of false negatives, you decrease the amount of false positives and vice versa. And this is how you do that. You simply change the significance level. But will they be inside or not? It depends on the bad guys. And we know anything about the bad guys. We don't know anything about the bad guys in this case, right? So that's one of the tricky things here. When one class classifier is good to use? Apparently, first of all, it's good to use when you have only members of your class. You don't have strangers. And the second thing is that you use it when strangers are very diverse. Imagine that, for example, you want to classify fake medicine. You want to distinguish between genuine medicine and fake medicine. Apparently, genuine medicine is produced by following certain production standards, right? So it means that the tablets produced on the genuine factory will be very similar, for example, chemically to each other. But the ways to produce fake medicine are very diverse. You can have, for example, small amount of active substance, or you can have probably no active substance at all. You can have different fillers. So it means that there is a very big diversity of the strangers. So in this case, one class classifier will be the best. Okay. Sometimes one class classification is also called authentication. So you try to find out if it's a member or not, and you don't care if it's not a member, you don't care which class it came from. Okay. Again, I tried this for iris data. In this case, I made 3 confidence ellipses, 90%, 95%, and 99% only for iris data. You can see definitely the size is different. And then if I compute, for example, number of false negatives and false positives, you can see that, for example, this is the worst case. You have a lot of blue points inside, so it means that you have a lot of false positives, but you don't have any false negatives, right? In this case, for 95%, you see, again, you don't have any false negatives, but you have 3 false positives, and then here you have 2 false negatives and 2 false positives. So from the accuracy point of view, these two are more or less the same. No, this is the best from the accuracy, right? The total amount of wrongly classified samples. But if you think about false negatives, false positives ratio, for example, this method gives you the smallest number of false positives, right? So that's actually it. Summing up, we talked about classification in general, what classification is, what kind of tasks you can solve using classification, meaning clustering, one class classification, and also discrimination. You know how to find the classification error, false negatives and false positives, and how to compute different statistics based on the classification error, meaning sensitivity, specificity, and accuracy, and how to compare classification models by the ROC curve. And then we also considered several state-of-the-art methods. In the next learning sequence, we are going to talk about how to use projection-based methods also for classification.